Okay, so the plan for today is to finish up these last couple of bits of 2, 1, and 2, 2, and then move on to 2, 3, solving equations with variables on both sides of the equation, with actually with constants and variables on both sides of the equation. The quote of the day, this is kind of a long quote from P.T. Barnum, the famous circus guy. But the kind of relevant point is here, true economy consists in always making the income exceed the outgo, and we always prefer a margin in favor of the income. And, Barnum is likely talking about, say, finance or economics, something like that. And it's not always, feasible, especially when you're a student, to make the income exceed the outgo. But I think this idea applies more generally in life. So personally, I find that when I build margin into my day, things go a lot smoother. I'm a lot less frustrated, a lot calmer than when I'm like, right on a razor's edge. If I have to be somewhere at a certain time and I leave with just enough time, I'm frustrated with all the other drivers on the road. I'm, maybe not making the best decisions. But if I leave myself 5 minutes, that might mean closing Facebook early or not watching another YouTube video or something. Then I make much better decisions. And I think margin in life generally is very important. How does this apply to, something like a math course, a general college course? Well, if you wait until, Sunday at 9 p.m. to do the homework that's due Sunday at 11:59, you leave yourself very little margin. Or especially if you're looking at one of the exams and you wait until the last minute to start that exam, you're really leaving yourself very little room for error. If anything goes wrong, you're going to miss that exam. That's going to be a huge hit to your grade. If you build in some margin, if you schedule yourself for the exam a couple days early, if something goes wrong, you've got a couple of days buffer. Or if you if you're writing a term paper, if you think it's going to take you 6 hours to write it and you wait until 6 hours before it's due to start writing it, you're really hoping that nothing goes wrong, that there's no power outage, that nothing pops up, that you didn't underestimate the amount of time it was going to take you. But if you started 2 weeks ahead of time and something comes up, you've got plenty of margin. And this is something that certain days I do better at than other days. Building margin in, but and I think everybody's going to be like that to an extent, right? Everybody's going to have better days and not so great days, but what I like to say is that when you have margin, what would be catastrophes become inconveniences. When you have no margin, what would have been inconveniences become catastrophes. So just something to kind of keep in mind with things like study skills and approach to coursework is, start it early, and you're going to have a lot more margin built in, and you're going to have, I think, generally have a better time with it. And the plus side is also that you just learn a lot better when you're not kind of under the gun, super stressed out. When you're trying to just get through the problem as fast as possible, it's going to really be hard to retain that information. If you do, 30 minutes, an hour of work every day consistently over a whole week, that's going to be much better for that, like spaced repetition and all those good things that really help cement ideas in your head. So just some thoughts for today. Okay, so wrapping up just these last couple of small details in 2.1 and 2.2 from last week. So we didn't talk to to too much of an extent about solving word problems. We really didn't talk about solving word problems at all, but we would, read the equation. So we kind of went from the kind of symbolic version, 5 times x minus 1 minus 2x plus 5, to a verbal version where I would read it, and then we would solve the symbolic version. What if we only have the word problem, so to speak? And I know a lot of folks really don't like word problems. They'd rather have the symbolic version directly. But it's really only one extra, usually pretty straightforward step to get the words into symbols. Now, if we have a legitimate like application-based word problem, those can be a few extra steps, but this is kind of, a more straightforward word problem. So 12 less than x is equal to 17. And one of the things we're looking for is keywords. So remember, an equation is a statement of fact about two expressions, how they relate to one another, that one expression has the same value as another expression. So I want to know where to put my equal sign first. That's what separates the two expressions. And is equal to is a pretty obvious one, but sometimes is equal to is just shortened to the word is. So if we see the word is, or the word is equal to, or the word equals, that typically means put an equal sign there. So this bit gives me the equal sign. Now, is equal to what? Let's start with the right-hand expression. And obviously, this is pretty straightforward. This is just the number 17. So quite a simple expression. It's just a number. But we could have had, x minus 17 or 3x plus 17 or something on the right side also. But in this case, just 17. And the other expression that's on the left side is 12 less than x. Now, we have to be a little bit careful. We might be tempted to do something like just copy this verbatim, 12, and then say, oh, less than, that sounds like minus, and then x. But if I have if my friend has $20 and I have $12 less than them, I have $8, right? So I take their amount minus what I have less than them. So 12 less than x means I start with x, and then I lose 12. So this is actually x minus 12. So there are some nuances like this. We just have to be careful with the grammar and with the details, with the nuance of the structure of these phrases when we translate from the grammatical phrase to the mathematical expression. But, another way you can kind of check yourself on this. If you're like, wait, 12 less than x, is that x minus 12 or 12 minus x? Put a number in for x, right? If I said 12 less than 20, well, I kind of intuitively know 12 less than 20 is 8. And if I did put 20 in for x down here, 20 minus 12 is 8. Now, that's not the solution to the equation, but we're just checking that we got the expression correct. If I had mistakenly done 12 minus x, I'd have 12 less than 20 for my example. I know that should be 8, but I'd have 12 minus 20. Well, that would seem to give negative 8. I think something's a little backwards there. So we translate it to an equation. And now we'll solve. Again, we want to get the x, the variable by itself. We do that by adding 12 to both sides. X minus 12 plus 12. The minus 12 and plus 12 cancel. 17 plus 12 is 29. And that's our answer. So jumping down to section 2.2, I'll go through this one as well, and then we'll go over and we'll do the practice problems for you to work on and touch base as a class. So this is kind of a capstone problem maybe for sections 2.1 and 2.2. And this is a pretty complicated looking equation, right? There's a lot going on here. We have some fractions, we have lots of parentheses everywhere. So it's easy to look at a problem like this and just not know where to start, or get overwhelmed, or just say, oh, this looks too hard to do. But there's a saying that a journey of 1,000 miles starts with a single step, right? Can I find one thing that I can do to work my way towards a simpler problem? What's one thing that I can do? Anybody have an idea?
You could start with the parentheses.
Exactly. Yeah. Let's start with simplifying the parentheses, and even more specifically, maybe even that's a bit complicated because I have 3 parentheses. I could start with this. 5 times parentheses x minus 1, I know that I can distribute that 5 into the x minus 1. I'm going to take this one step at a time. Now, if you're a little more fluent with this, you can do multiple steps in one, multiple operations in one step. That's perfectly fine. Just make sure that you're doing everything correctly and keeping track of everything. But I'm going to do it one operation per step, just to show you that if we break this into really small chunks, we might end up writing a little bit more. We might have to write a few lines, but it's not insurmountable. So the 5 distributes into the x minus 1 as 5x minus 5. And now I'm just going to copy everything else down, right? Minus 2x plus 5 equals 4 times x minus a half minus 4 times x plus 1/4. And I can do the same thing. I can look for, is there another parentheses to simplify, right? PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. Well, I do have this 4 times x minus a half. This is 4x minus 4 times 1/2. I'll worry about simplifying that later. And then the left side, I'm just going to copy the whole thing down. On the right side, I have another parentheses I can simplify. Now, I ran into a 4 times a half. Maybe I'll just simplify that now. If you wanted to, you could do it in a future step, but I'll take care of this now. 4 times a half. What's 1/2 of 4? Well, that's 2. I want to be super careful here. I have a minus 4 that I need to distribute. So I want to make sure that negative sign comes along. So I have a minus 4x minus 4 times 1/4. And one more line. And then 4 times 1/4 is just going to be 1. That's after a minus, so minus 1. I've gotten rid of all my parentheses. So I took my first step in the order of operations, my parentheses. I've kind of gotten rid of them all. I've got all of my terms individually listed now. And now I can look to do something else. What's the next thing that I could do? What's the next kind of strategic goal that I could work towards to make this a little simpler?
You can combine like terms.
Exactly. I can combine like terms. And maybe the first thing that I'll do there is on each side of the equal sign, I'll kind of put all of my terms with x in front and all of my constant terms at the end. So I have 5x. In this expression, do I see any other x's? Yeah, there's a 2x, a minus 2x. And then I have minus 5 plus 5. Well, those actually go away, right? Minus 5 plus 5 just adds to 0. On the right side, if I put my x's together, I see that I actually end up with a 4x minus 4x. Those go away. I have one thing minus the same thing. They cancel. And then minus 2, minus 1. Just being careful with all of my signs and all of that, making sure that I don't drop any of my negative signs. And now I can combine like terms. I see that on the left, I have 3x equals -3, -2 minus 1 on the right. And I can divide both sides by 3 to get x equals -1. I went a little faster at the end here. But really the thing that I wanted to point out is that kind of the scariest part is this beginning where there's just so much going on. But we can take it as slowly as we want to, right? We can do one step at a time. and just go through step by step and just chip away at the problem. And the big problem doesn't seem so big anymore whenever each step is just, one manageable operation. Now, again, when you get used to this and you say, well, hey, wait, could I do this distributive property and this one in the same step? They don't really directly interact with one another. And sure, absolutely, you could. That would be quicker to do. And when you get more comfortable with approaching problems like this one, just problems similar to this, you absolutely can do that. You can recognize, okay, there are kind of 3 distributive properties that I'm going to need to do. None of them like directly interact with another one. It's not like I need to do this one before I do that one, or it's going to mess something up. So sure, you could do all 3 of them in one line when you get, more comfortable with it. But my point is that if you get to a problem like this and you look at it, you say, oh, geez, that's just overwhelming. Just look for one thing you can do. I can distribute the 5 into the x minus 1. I can do that. And then just do that and then see where that gets you. And then look for one more thing you can do. Maybe instead you would have kept working on the left side. Maybe you would have combined like terms on the left side and then move to the right side, right? There's not a specific order you have to do these in. This is the order we did them in. If you wanted to kind of chip away at the left side till the left side was simple and then work on the right side, that's perfectly okay too. Okay, so here are 2 problems, or 2 worksheet problems for these 2 sections. So if you want to take, let's say maybe 4 minutes, because that second one I think is going to have, a few operations to work through. So we'll take, let's say 4 minutes, work through these 2 problems, and then come back and we'll touch base. Okay, let's take a look at these two. So for this first one, there's kind of a word problem component, but we're given the equation to solve at the end. But let's see where that equation comes from. So we have a 7/16 inch diameter lag bolt, or a big screw, and we want to drill a pilot hole. The bolt should be an 1/8 inch larger than the hole so that the threads grip properly, right? If we drill a hole the same size as the screw, then the screw just kind of slides in and out. It doesn't actually like screw in and hold. We want the screw to be bigger than the hole so that when we screw it in, the threads will grip on the wood and hold the screw in. So I have my lag bolt that has diameter 7/16 of an inch. And I want the bolt to be 1 inch larger than the hole in diameter. So this will be the hole, and it has to have a diameter D, which we will find. But in particular, we want the hole to be 1 inch, or sorry, 1/8 of an inch smaller in diameter than the bolt. So I see that I have to take my diameter of the hole and add a little bit to reach the size of the screw. And what I want to add to reach the size of the screw is 1/8 of an inch. Okay. So on one hand, this width here, on one hand, I can say that this width has to be D, the diameter of the pilot hole that I'm going to drill, plus 1/8. But on the other hand, that same width has to be the width of the lag bolt, the screw, which is 7/16. So that's where we came up with these two expressions, D plus 1/8 and 7/16. And that's why we're equating those two things. So if we have a picture like this, a lot of times it's really helpful, or sorry, if we have a word problem like this, a lot of times it's really helpful to draw a picture if that kind of applies. If it's anything that's geometric or that's kind of physical like this, even if you're not a great artist, like I'm not, just having a diagram can help you keep things sorted out. You know, wait, is it D plus 7/16 equals 1/8, or is it, you know, having a diagram helps you keep sorted out like which bits go together. Another thing we can do is we can just get an intuitive idea for what the size of our answer ought to be. Well, we kind of intuitively understand that, well, D has to be bigger than 0, right? I mean, it wouldn't make much sense to drill a pilot hole that was negative, you know, 1/2 inch diameter in size or something like that. And we also know that D has to be less than 7/16. So we can also bound our answer. We can give ourselves a way to check our answer. So we can, when we get our answer, we'll check, is it positive and does it seem like it's less than 7/16? Okay, so our first step, just subtract 1/8 from each side. And this gives us D equals 7/16 minus 1/8. I need to add or subtract two fractions with unlike denominators. I look for lowest common denominator, and I see that this is a pretty straightforward one. If I multiply 8 by 2, I get 16, and then I have a common denominator. So I'll multiply 1/8 by 2 over 2 to give me 7/16 minus 2/16. And I'm going through this a little quicker than we did last week because, again, after the kind of the prerequisite review from last week, hopefully you've kind of brushed up on some of this material, and this should move a little more smoothly. But of course, if you're stuck on this part or something, or if you don't see where this came from, one of the good things to do is to mark that in your notes. And then when you're reviewing your notes, maybe later today or tomorrow, go back and fill in the details of this problem so that you make sure you see exactly where all of this comes from if you don't see that right away. And then this gives me 7/16 minus 2/16 is 5/16. This is a positive number, that's good. And it's less than 7/16. That's also good. We've, in a sense, checked our answer. And we would want to grab a 5/16 drill bit to drill our pilot hole. Okay, in the second problem, solve the equation. We'll do this one a little faster than we did the previous one. I did the previous one, very much like one operation per step. There was some extra writing. It's a little less efficient, but, if you get overwhelmed, that's a good place to start. Here, we'll do a couple operations per step. And just to show you how efficient this can be when you get used to it. But I would recommend, again, mark this in your notes and hopefully you've gone through and you've kind of worked through to a solution, but mark it in your notes and maybe come back to it and ask yourself, okay, can you do it in one fewer step than you did it previously, right? Can you maybe make things just a little bit more efficient? Can you get a little bit more comfortable with working with these operations? But the first thing that I'm going to do is I'll do all of my distributive properties in the first step. None of these distributive properties I have to do, none of these multiplications interact with one another, so I can do them all at once. So here I have 6x minus 6 times 2, or that's 12. I'll just copy these down. Plus 3x plus 12 equals, now from this distributive property, 4x minus 4. And from this one, again, I have to be very careful with the minus 4x minus 4 times 2 is minus 8. Now, if these were harder multiplications or something, we could always, instead of going through and writing an entire step just to do, say, one small operation, we could always jump over here to, say, some scratch work and, work on that operation off to the side and then copy it back over. So that's another kind of, intermediate option between the two. So between, writing out a new line for every operation or every step and, not writing out any extra lines for a lot of these steps. If we have something that's a little complicated, or maybe even like -4 times x plus 2, we could come over here off to the side, do a little bit of scratch work, and then copy it back over. So that's another option. Okay, I got rid of my parentheses. I now know that I want to combine like terms. I think I will take an extra step just to get everything sorted out, because this is an area where I can easily get a sign wrong or something like that. So I have 6x plus 3x minus 12 plus 12. They go away. They cancel out. Then equals 4x minus 4x. We see that they go away as well. They cancel. And then I have -4 minus 8. And exactly in chat, exactly 9x equals -12. And now we've gotten ourselves back to an equation that's pretty straightforward to solve, right? It took a little work to get to this point, but at this point we say, okay, I recognize how to solve this equation. Maybe I didn't recognize up here that I was going to get something that looks like that at the end, but I just kind of took a step or two at a time and worked my way to something simpler than that, something even simpler, until I get to something that I recognize and I say, oh, I know this pattern. I've seen this pattern before, and I know how to solve these. Math it can be a lot of pattern recognition and saying, hey, I saw something before that looks like this. In fact, I've done a problem that looks kind of like this, 30 times now, and I know how to solve this. So I divide by 9 on both sides, and I get x equals negative 12 over 9. And then I'm going to look for common factors. So this is going to be negative 4 times 3 over 3 times 3, and those 3's divide out. This gives me negative 4/3. I would typically leave this way, but we could also say negative 1 1/3 if we wanted to turn it into a mixed number. Okay, so any questions on those problems?
I just have one quick question.
Yeah, sure.
So for the last equation that we solved, if we didn't simplify it, would we still get any credit for that, or would that be like a
So like if you left it at negative 12 over 9?
yes?
Yeah, so in WebAssign, it would depend on how the question's asked. So it's always a good idea to simplify as far as possible. In WebAssign, it kind of depends on the question.
Okay.
But that being said, if it was on a homework, if you get it wrong, look and make sure that things are simplified. If it's on an exam where you only have one shot, little tangent about exams is every time that for every exam, after the due date for the exams, I go back through and I look at anything that WebAssign is marked wrong. And I review, every question for every student that WebAssign is marked wrong. And then I make a judgment call, right? So if I went through and if WebAssign wanted to say this answer, but you gave that answer, most likely, let's say it's a 5-point problem, I'd probably give you, 4 out of 5 points, or maybe even if it was a longer problem and you got all the way to this point but didn't simplify, I might even just give you the full credit for it if I didn't think that like simplifying was really a big enough portion of the problem to take off a whole point. I usually don't do half points or anything like that. I think that's just starting to split hairs a little too much. But yeah, so if it was on an exam or something, when I review the exam, I would see, okay, this is just an issue where that last little step, the 3's weren't divided out. It wasn't put in lowest terms. So you would get, most of the credit, perhaps all the credit for that problem. Now, of course, if it's kind of the crux of the problem, if the whole, if it's, an earlier problem and essentially the whole purpose of the problem is to put a fraction in lowest terms, that, that might change that balance a little bit. But for a problem like this, where there was a whole bunch of other operations we need to do to get this point, you'd get something like 4 out of 5 points for this.
Okay, cool. Thanks for the clarification.
Yeah, definitely. Any other questions?
I have more of a comment. I got on a little bit late. Are you recording it?
I can hear you talking, but there's a lot of noise in the background. I can't really hear what you're saying. Can you type your question into chat? I don't hear you now. So yeah, if you could type your question into chat, I do have chat up, and I can I can answer your question if you type it in there. Okay, if I see the question pop up in chat, we could always just come back and kind of revisit it. Okay. So let's look to generalize this a little bit. We looked at the general method to solve x plus a equals b last time. We just subtracted a from both sides and we got x equals b minus a. What about x times a equals b, or ax equals b? Here x is a variable, a and b are constants, and we will have to include one extra assumption that a is not 0. of course, if A was 0, I just have 0 times x equals b, or just 0 equals b. And that's not really a linear equation, is it? It's not. So if I just say 0 equals b, well, that's either true if the constant b that was chosen is 0, or it's false if the constant b that was chosen was not 0. So there's really nothing to solve there. If I just say 0 equals b, solve for x, like there's really no x's there. So we need an extra constraint here. So if I have ax equals b, if I have an equation that's kind of in this form, if I see this pattern, my strategy is I divide through by a on both sides. I'm going to put implies here, this kind of thing that looks like an equals, but with an arrow to the right. And I have x equals b divided by a would be my solution to this general structure of linear equation. Yeah, if we were thinking of this in terms of a graph, maybe something like ax, we would think of a as maybe being the slope, but I would stay away from that at this point, because really when we're thinking of things like slopes and intercepts and graphing equations, we're really thinking of linear equations in 2 variables. So if I had like y equals ax and y and x were variables, then I would have something that's a little more along the lines of something that I might want to graph, or I might want to talk about a slope or something like that. Yeah, so we have x equals b over a is the solution. And it was a good thing I said above that a is not 0, because that keeps me from dividing by 0. Again, one of the really powerful ideas in mathematics is we can take problems like these past ones that we've looked at. We've gone through many of these problems now, and from those specific examples, we can maybe abstract away from the specific examples and then develop a general concept, a general understanding, a general idea that when I see this pattern, I do this thing, and that gets me the solution, right? It's a lot like chess. Chess is a lot of pattern recognition as well. It's like, oh, when I first learned what a fork is, it was really hard for me to see, like, wait, can this pawn actually fork those 2 pieces or not? Or will I try to like fork a bishop and a knight, and the bishop just takes my pawn? Like, or does it actually work? Does it actually win me one of my opponent's pieces? Really hard to see at first, but after you have seen that same idea in 50 or 100 different situations, and you've done it correctly sometimes and done it incorrectly other times, and you get that instant feedback when your opponent, like, captures your piece or checkmates you or something, or when you capture their piece, you get that instant feedback. And then you say, oh, okay, I recognize this pattern more readily, and I'm able to figure out the tactic. What's the next step more quickly? So a lot of this is, working through problems, spending the time with the material, drilling the problems, so that you really develop that intuitive pattern recognition. And so the things like this take place a little more intuitively, and you don't have to think as much about them. Okay, so moving on to the next section, 2.3. And just a little quick note, 1-step versus 2-step equations. The equations we've covered so far, what we might call 1-step equations. So, x plus 3 equals 11. And I'm going to use this implication sign again, just to say that these 2 things are kind of equivalent. I can do 1 step, subtracting 3 off of both sides to get x equals 8. 1 step, and we don't really count things like simplifying and things like that as an independent step, but like 1 equation solving step. Or if I had, 5x equals 7, I can divide by 5, and I get x equals 7/5. Again, 1 equation solving step to do these problems. Now, even a problem like this, there are a lot of steps in a sense, But most of these were just working with each expression individually, right? They were simplifying the right-hand side expression or simplifying the left-hand side expression. Most of these steps weren't really equation solving steps. They weren't inherently using the fact that we have two things that are equal to one another. In other words, most of these steps, if I just gave you, say, this expression in isolation and said simplify it, that would be what this step was, what that step was. It doesn't matter that that expression is part of an equation for those steps. So we're talking about a one-step or a two-step equation. We're kind of talking about equation solving steps. But here we got to this point, and this is really where we used the fact that we had an equation. We divided both sides by 3. We kind of did something simultaneously to both sides. That was an equation solving step. So this was still a one-step equation, even though getting to the point where we could apply that single equation solving step, that was a lot of work. But still just one equation solving step, just one step where we said, do the same thing to both sides. So now we're going to start looking at two-step equations. So equations where to solve them, we'll have to do one equation solving step, to do something to both sides, maybe do a little simplification, and then do another equation solving step, another operation where we do the same thing to both sides. So we're going to start with this one. And I've kind of used these kind of same two problems to kind of build off of or to riff off of for the different variations we'll look at. So here I have solve 3a minus 1 equals 11 for the variable a. So this doesn't really look like ax equals b. It doesn't really look like a plus x equals b or x plus a equals b. I guess maybe I shouldn't be using a and b with x because I have a as my variable here, but it doesn't look like x plus number equals number. It doesn't look like number times x equals number. But it kind of does look a little bit like variable plus or minus number equals number. If I think of 3a as just kind of like the variable term, I see I have a variable term, kind of plus or minus constant term equals constant. So if I think back to my pattern from last time, if I have something like this where I have variable term plus constant term equals constant term, I wanted to subtract off the constant term that was on the side of the equation with the variable. So this is really where that idea of abstracting away from the details and understanding a pattern. I have like a variable term plus or minus a constant term equals a constant term. The way that I solved that type of problem last time was I moved the constant term, in this case on the left, the one that was attached to the variable, over to the other side. I got my constants all to one side. Oh, yes. Yeah, somebody asked in chat, do we record a class? Yeah, I record every class. So, I mean, so long as I remember to, every once in a great while, I forget to start the recording, but yes, definitely it is recording. So you'll be able to go back and reference if you miss something, or if you just want to review the lecture, want to review a problem or something. But yeah, so we have variable term, say plus or minus a constant term equals constant term. That general structure, the way that we approached that before was we got rid of the constant term that was attached to the variable term. Now, again, this isn't exactly the same type of problem. We have 3 times a variable instead of just the variable, but I wonder if that same first step would help me to make progress here. In other words, I wonder if taking the step where I try to get rid of this -1 from the left-hand side, or this -1, might move me forward. If I want to get rid of that -1, I have to add 1 to the left. And because it's an equation to keep things balanced, I also have to add 1 to the right, right? If I put, 1 pound mass on the left side that of the scales that are already balanced. I have to put a 1 pound mass on the right side to keep it balanced. On the left side, the -1 + 1 cancels, and I'm left with 3a. And on the right side, 11 + 1 = 12. And I see, indeed, this did actually move me forward, right? Because now I have a type of equation that looks exactly like this one, where I have constant times variable equals constant. And now I know how to solve this. I can do another equation solving step. I can divide by the constant that's multiplying the variable, in this case 3. 3a divided by 3, the 3's will cancel, and I'm left with just a. I guess technically the 3's divide out, and I'm left with a. 12 divided by 3 is 4. So I really wanted to drive home the idea that that understanding patterns and structures, abstracting away from the details and developing these general ideas like this, or like the previous one for x plus a = b, really led me to a method of solving a problem that didn't fit cleanly into either of those. But because I recognized some semblance of a pattern, I had an idea. Now, sometimes you might see some semblance of a pattern, try an idea, and it doesn't work. That happens. But in this case, the idea did work. It got me to an equivalent equation that was simpler, and that I did know how to solve immediately. Similar idea on this next one. I have a variable term plus a constant term equals a constant term. I don't just have variable plus constant equals constant, but I have a variable term. Again, maybe I can apply that same strategy. Can I get the constant terms all together on their own side, keep the variable term by itself, isolate the variable term, that 5x, get the 5x by itself, and then see where that gets me? I can subtract 7 from both sides. 5x plus 7 minus 7, 5x. 4 minus 7 is -3. And now I've gotten myself to an equivalent equation that I know how to solve directly. I know I've seen this exact pattern before many times, and I know I divide by 5. I do that on both sides, and I get x equals -3/5. And just a little side note about negative fractions is -3/5 is the same as 3/5 is the same as -3/5. These all mean the same thing. So just something to recall from before, that that folks, occasionally get a little messed up. But whether the negative is in the numerator, in the denominator, or in front of the fraction, it's all the same fraction. You can kind of think of moving the negative from the numerator to the denominator just by multiplying by -1 over -1, and kind of multiplying through. Okay, so let's pop over here then. We have 2 practice problems over here. So again, I'll give you maybe about 3 minutes to work through these 2 problems. We're going to, speed things up just a little bit now that we're kind of getting used to some of the arithmetic operations. So work through these 2 problems on your own, and then we'll touch base in about 3 minutes to go over them.
I think I need to stop. I did hear somebody, I think, ask a question, but
I think you're still having trouble with audio. Yeah, there's still a lot of static in the background, and I can't really make out what you're saying, but I think you messaged me in chat, and I think I answered the question about recording. And of course, if you ever need extra help on any of these problems or anything that we're going over, I have office hours right after class, or also on Monday and Wednesday. So that's definitely always an option, or send me an email or anything like that. There's all of those options for any extra help that you might need.
Okay, thank you.
Okay, it's been about 3 minutes, so let's revisit these two problems. So again, we see this general structure where I have a variable term, plus or minus a constant term equals a constant term. I want to get the variable term by itself. The idea is to what we might call isolate the variable or isolate the variable term. So I'd like to get to a structure where I have stuff with variables equals stuff with constants, or variable terms equals constant terms. I can get this for this variable term by itself by adding 7 to both sides. 4a minus 7 plus 7, this gives me 4a. 9 plus 7 is 16. And now I have a structure that I'm very familiar with. Number times variable equals number. And I know I just divide by the coefficient of the variable, divide by that factor that's multiplying the variable. Remember, terms are things that are added or subtracted from one another, and factors are things that are multiplied or divided together. So 4 divided by 4, they go away, and I'm left with a on the left side. 16 divided by 4 is 4. And for the second one, again, similar pattern, similar structure. We're going to take a similar approach. I'm going to look to get this variable term, 14x, by itself. I'm going to do that by subtracting 1 from the left side, and then to maintain balance in the equation, subtract 1 from the right. 14x equals 8 minus 1 is 7. And again, I know how to solve this kind of equation. I've seen this pattern a bunch of times. Number times variable equals number. I divide by that coefficient in front of the x. And I get x equals 7 divided by 14. I know the 14 is 2 times 7, so I get to cancel a factor of 7. And I see that x equals 1/2 is the answer. Okay, so let's look at these problems. So these next two, let me space these out a little so that that next one isn't on the screen. There we go. If I take a look at these problems, I might be tempted to do the same thing I just did. As I see, oh, okay, I have on the left side, I have a variable term plus or minus a constant term. Just get rid of the constant term on the left-hand side. But notice that the pattern is actually a little different. I have variable term plus or minus constant term equals variable term on the right-hand side. Up here, I had variable term plus or minus constant equals constant on the right-hand side. So if I have variable plus or minus constant equals constant, I want to add or subtract the constant on the variable side to get rid of it, to get it off the variable. But down here, I have variable, say plus constant equals variable. If I move the constant to the other side, I didn't really do anything. Then I have variable equals variable plus constant. That doesn't help a whole lot. So here, what I recognize is that the way that I get my variable terms together on a single side is to actually move the variable term. And this can seem a little strange. We haven't actually done problems where we've moved the whole variable term before, but the operation is just the same as moving the constant term. And when I say moving, I just mean in this sense that, you know, adding 1 to both sides, we're kind of putting that 1 over on the right side with a different sign, or subtracting 7 off of both sides, we're kind of putting that 7 on the right side with a different sign. We've moved constant terms before a bunch, but here it seems like the strategy is going to be to move the variable term to the other side. Now, how do we do that? Well, we do it with the same process. We have a 3a on the left side, but I don't want that 3a on the left side. I'm just going to subtract off 3a from the left. I'm just subtracting a different term. Instead of subtracting a 7 from the left side, I'm just subtracting 3a from the left side. The same rules apply. If I subtract 3a from the left side, I have to subtract it from the right side as well. 3a minus 3a, that cancels, that just goes away, and I'm left with only the -1 on the left side. On the right side, for a minus 3a, we could write this as 1a. And I had a couple of people ask about this over the weekend. When we have 1 times a variable, we just omit the 1 and we just write the variable. And we actually noticed that that one operation and some simplification got us the solution. So this turned out to be a one-step problem. We only had to do one equation solving step, one operation where we did it to both sides to get the solution here. We can look at this next one, for example, 5x plus 7 equals 6x. And we see the same thing. We have a variable term plus a constant term equals a variable term. Again, I want to isolate my variable terms. I want to get my variable terms all on one side, away from the constant terms. I do that in this case by subtracting off the variable term on the left side. So by doing a minus 5x, that breaks this variable term off of that constant term on the left side. I have to do that to the other side of the equation as well. And I see that I'm going to end up with just constant terms on the left side, or one constant term in this case on the left side, and variable terms, two variable terms on the right side. 5x minus 5x, that just goes away, that's 0. And then plus 7 equals 6x minus 5x is 1x, or just x. So again, in this case, we happen to be able to solve this one with a single equation solving step. And we got our answer, x equals 7. Okay, so let's work on these next two. So take a look at these two. I'll give you about maybe 2 minutes or so to work through these. I think these will be a little quicker than some of the previous ones. So we'll do about 2 minutes, and then we'll come back in 2 minutes and work through these.
I have a question at the end of the class. Sorry for all the background noise.
I can actually hear you better now. So yeah, if you want to stick around at the end of the class, yeah, that's fine. We can definitely chat then.
Okay.
Okay, so let's look at these next two problems. And again, similar structure as before, we have variable term plus or minus constant term equals variable term. We want to get the variable terms all together on one side, the constant term or terms all together on the other side. And we'll do that here by moving this 7a to the other side. I'll subtract 7a off of the left side. And if I do it to one side, I have to do it to the other side as well. 7a minus 7a is 0. Minus 1 gives me -1 on the left side. 8a minus 7a gives me 1a, or just a, on the right side, and I'm done. So nice little one-step equation is what this turned out to be. It turned out to be a one-step equation in this case. And I get my answer, a equals -1. And again, same pattern on this next one. Variable term plus or minus constant term equals variable term. I want to get my variable terms on one side, my constant terms on the other side. On the left side, 15x minus 15x is 0. And I'm left with 7. On the right side, 16x minus 15x is just x. So I have x equals 7 as my answer. Any questions on either of these? I think these ones were maybe a nice little break, somewhat straightforward relative to some of the ones we've done recently. Okay. So now let's build up a little more. We have these next two problems. Let me try to keep this one on the screen up here so we can refer back to it. We have these next two problems, and these look qualitatively similar, right? I have a variable term plus or minus constant term equals variable term. Similar pattern. It's going to turn out that these will be a little bit more complex, but that same first step is going to work to get us to a simpler equivalent equation, but not quite all the way to the answer in these cases. But we do still recognize the pattern, so we're going to try to apply the same first step. I want to get my variable terms on the same side, my constant term or terms on the same side, and I see that a good first pass is going to be to subtract 3a to get rid of this 3a on the left side, so that I'm just left with a constant term on the left side. If I do that to one side, I need to do it to the other side. Now I can simplify a bit. 3a minus 3a is 0, minus 1. Our left side turns out to be -1. My right side, when I simplify it, 10a minus 3a is 7a. We're not quite at a solution yet. Up here, we happen to kind of luck out in a sense, where our right-hand side kind of turned out just right to where we didn't have to do another step. We got something like 6x minus 5x or 4a minus 3a, and we were just left with the variable by itself. But that was kind of a special case of this structure. However, I've gotten myself to an equivalent equation that, again, now I recognize this pattern and I know how to solve this equation. I have constant times variable equals constant. How do I solve this? I divide by the constant that's multiplying the variable. I better do that on both sides. 7a divided by 7 is just a. -1 divided by 7 is -1/7. Which again could be written as -1/7, or you could even write it as 1/-7. Probably be unlikely to do that in this case, but if you wanted to write it as -1 divided by 7, that's perfectly okay too. So this is what we would call a two-step equation, because we had to do one equation solving step, then a second equation solving step. Similarly down here, this next one, 5x plus 7 equals 12x. What kind of terms do we have? We have a variable term plus a constant term equals a variable term. I want to get my variable terms all on one side, my constant term or terms all on the other side. So I see that I can do that by subtracting 5x from the left. Also doing that to the right. 5x minus 5x is 0, they go away. I'm left with just 7 on the left. And on the right side, 12x minus 5x is 7x. I've done one equation solving step. I've done one thing that I've done to both sides. I don't have quite a solution yet, but I've made a heck of a lot of progress, right? 7x equals 7. This is a pretty easy one to solve. I divide both sides by 7. On the right, 7x divided by 7 just gives me x, and on the left, 7 divided by 7 is 1. Okay, let's do a couple of these practice problems. So if you want to work on these two problems, and then again, we'll touch base, and let's do, again, maybe about 2 minutes for these. We'll pick up the pace just a little bit here because these ones are a little more straightforward than the ones that are coming up. We'll have a little more time for those more complex ones. So 2 minutes and we'll touch base. Okay, let's take a look at these. So again, we have the same structure, variable term plus or minus constant term equals variable term. What's the first step that we want to do here? Anybody come up with the first step?
Subtract 7a from the left and to the right.
Exactly. Subtract 7a from both sides, from the left and from the right. 7a minus 7a is 0. Left with -1. And the right side, we simplify, right? 15a minus 7a is 8a. We've done one equation solving step. We're not quite at a solution. What's our second equation solving step? Just divide by 8. And we get a equals -1/8. It's kind of a messy a there, but and same structure for the second one, right? Just subtract 5x from both sides. 5x minus 5x is 0, plus 7 is 7, equals 11x. And then we divide through by 11. And we see that x equals 7/11, 7/11. So at this point, and this does tend to happen, at this point, we kind of used previous simpler patterns to help us kind of guess a strategy for this new pattern. And at this point, this kind of new pattern like kind of becomes ingrained as its own pattern, and it can serve as a foundation for giving us strategic ideas to solve more difficult problems, right? So we can build the complexity like this. And I think this, I don't know why it keeps popping me to the top of the page when I switch. Yeah, usually doesn't do that, but so this is something that that can make math kind of challenging, is that, you know, we had a couple of very basic structures. We built on those to get a slightly more complicated, slightly more complex structure. We're building off of that to move the next level up, and building off of that to move a level further, and so on. That means kind of, you know, if you're like climbing this ladder that's reliant on, you know, one foundational piece, if you're like one rung up some ladder or up some set of steps, like, okay, as long as that one piece is firm, then you're good. If you're climbing a ladder or a structure or something that has 15 pieces all stacked up, if any one of those pieces is shaky, that kind of makes the whole thing shaky, right? At least from that point up. It's super important in a course like this not to fall behind, to make sure that you keep up with the work. Again, kind of ties into that margin issue. Making sure that you're kind of keeping up with the work, that you're drilling the problems, that you're reviewing this material every day. Super important for a course like this, so that you understand a given structure that we're going to use to build on to build the future structures. And that's what we're going to see here. Okay, so we now have a situation where we have variable terms and constant terms on both sides of the equation. And again, we haven't really seen this pattern specifically before, but we have seen variable term plus or minus constant term equals constant term. We know how to deal with that. We get the constants on the same side. We've seen variable term plus or minus constant term equals variable term. We know how to deal with that. We get the variables on the same side. Can we use those ideas to guess a strategy for a more complicated structure like this one, where I have variable and constant terms on both sides? Well, what I can extract away from those previous patterns, variable plus constant equals variable, variable plus constant equals constant, that really kind of what I wanted to do was I wanted to get the variable terms all together on one side and the constant terms all together on the other side. That was really what I had worked to do. So can I try to do that here? For this first one, I'm going to do it in 2 steps. And then for the second one, we'll kind of do it in kind of more one step. So for this first one, I'm going to try to just start by getting my variable terms on the same side as one another. And I'm not going to worry about the constant terms for right now. I just want, right now I have one variable term on each side of the equals. I want those 2 variable terms to be on the same side of the equals. That's going to be my first kind of baby step. And I guess I'll just move the 3a over to the other side. I'll put my variable terms on the right-hand side. Why not? We could do it the other way, I suppose, but we'll do it this way. Again, not worrying about the constant terms right now. On the left side, 3a minus 3a is 0. I'm left with a negative 1 on the left. On the right side, I have some variable terms to simplify. 10a minus 3a is 7a. Catherine, I've muted you a couple of times now because of the background noise. Would you mind just not unmuting yourself? If you have questions, you can always pop them in chat, or just to keep the background noise kind of from being a distraction. But if you have questions, just type them in chat, and I do have chat up and I can see them over here. Okay, thanks. So 10a minus 3a simplifies to 7a. And then we just have our plus 5. So at this point, we've kind of done half the work. We've gotten the variable terms on the same side as one another. So I've got my variable terms on the right side and then combine them together. And I've kind of worked my way back to a structure that's like variable plus constant term equals constant term. And again, I know how to approach this. I'm going to get my constant terms on the same side by subtracting that 5 to get that plus 5 off of the 7a, and to get my constant terms together on the other side of the variable term. So 7a plus 5 minus 5 is just 7a on the right-hand side. -1 minus 5 is -6. And now I'll do another equation solving step. Again, I've made my way to a type of equation that I'm very familiar with at this point. I divide by 7, and I get a equals -6/7. And that's my answer. Well, for this next problem, we see that we have a similar structure. Variable term plus or minus constant term equals variable term plus or minus constant term. I have variable terms and constant terms on both sides of the equation. And I know that my kind of strategy is to try to get the variable terms on one side of the equation together and the constant terms together on the other side of the equation. Here, I'll just do this in one step. If you want to do it in 2 steps, if you want to take an intermediate step, definitely go ahead and do that. Go back through your notes, kind of fill in some of these details, but we'll do it in one step just to show how that might look. Because the variable terms and the constant terms don't kind of directly interact with one another, I can handle them both in the same step. I'll try to get my variable terms on the right-hand side by subtracting 5x off of both sides. And at the same time, I'll try to get my constant terms on the left side, in this case, by adding 8 to both sides. And again, if you say, oh, this is too much going on all at once, well, go back through your notes, write it out in 2 steps. And, the 5th or the 10th time that you work through it in 2 steps, you'll get more used to how all these operations work. And, you can work your way towards doing it in 1 step then. But on the left side, I see the 5x minus 5x, they go away. And I'm left with just constants. 7 plus 8 is 15. On the right side, minus 8 plus 8, they go away. Well, let me cross it out that way, it looks a little better. 12x minus 5x is 7x on the right. So really, I've kind of done, just one equation solving step here. Or up here, I've kind of broke it into 2 equation solving steps for that same process. And again, that just depends on your comfort with the material. Don't reduce the number of steps and increase your error rate when you feel comfortable reducing the number of steps and you feel that you're not going to make additional errors. Then sure, go ahead and cut out a step here and there. But if it's necessary to keep your error rate low, always put in an extra step or so. That's perfectly okay. And again, we get to this number times x equals number that we are very familiar with at this point. We divide by the coefficient of the variable. We divide by the constant multiplying the variable. And we get x equals 15/7 as the solution. We'll save the general strategy for next time. And we'll do a couple of practice problems at the end of class here. So take about 3 minutes to work through these. 3 minutes might be a little bit tight on the time, but see how far you can get in 3 minutes. And then we'll touch base. We'll finish them up in the last few minutes of class, and that'll finish up class for today. Okay, let's take the last few minutes of class to work through these two problems. And then that'll wrap us up for today. So any thoughts on what the first step is for the first problem? You can either give me kind of the kind of baby steps version, like just one of the steps, or two steps at once. Either way is fine.
You would subtract 7a on both sides, and you would also subtract 4 on both sides.
Exactly. So subtracting the 7a on both sides is going to put our variable terms on the right side. And then we say, okay, how do I get the constant term off of the right side? I got to subtract 4 for that. That puts my constant terms on the left side. 7a minus 7a, they go away. -1 minus 4 is -5. 15a minus 7a is going to be 8a. 4 minus 4, they go away. So I've got my variable term equals constant term, and I divide through by the number multiplying my variable. In this case is 8. 8a divided by 8 is just a. And on the left side, I have -5/8. And that's my answer. So perfect. And for the last problem, if I wanted to do this one step at a time instead of two steps all at once, what would be, say, the first step that I could do? There's a few different choices here, a few different approaches we could take, but what would be one first step that I could do?
Subtract 5x on both sides.
Exactly. Yeah, we could subtract 5x on both sides. These go away. I'm left with 7 on the left, 11x minus 9 on the right. What would be my next step?
+9.
Exactly. Add 9 to both sides. These go away. I've got just my variable term on the right now. I've got 11x equals 9 plus 7 is 16. Variable term equals constant term. And I know when I get to this point, I divide through by the number multiplying my variable. 11x over 11 is just x on the right. 16 over 11 is just 16/11. That doesn't simplify, and that's our answer. Okay, so I'm going to stop the recording.